Hello everyone, here's Jonathan. So in lecture one, I'd like to talk about probability. So why do we need probability in general? So the classic answer is that randomness and uncertainty exist in our daily lives as well as in every discipline in science. So for example, there are many examples, but I'll give you two. For example, what is the chance of having twins? Second one, what is the chance of winning the lottery? Okay, so in any of those two cases, okay, you need to ask the question, what is the probability? What is the chance? That's exactly the same. And in order to understand how to compute the chance or the probability, you'll need some tools that you're going to study in class. Okay, and I'd like to start talking about those tools. So in general, when we are talking about probability, it's best if you think about it as a machine denoted as P. P to remind ourselves that we're talking about probability. And there is an input. The input is an event. Okay, the event, for example, can be, for example, if you look at the first example here, the event is having twins, and then we expect the machines to return an output, what output? A numerical value. And the numerical value represents the chance of having twins. So basically, when you think about probability, you should think about it as a machine again, that the input is an event, and the output is a numerical value that represents the chance of getting this specific event. Okay, so now in general, in this course, we'll refer to the term probability as chance. Okay, now we continue with four components of probability. So probability has four components. The first one is that, in general, we are doing an experiment. I'll give you an example in a few seconds. Next one is that the experiment has more than one outcome. And not last one, but there are two more. The outcome is unknown in advance. And last one, if we repeat the experiment, we won't necessarily get the same result. Okay. Now I'd like to show you an example. So that's a classic one. Okay. So for example, rolling a die. Let's see if those components hold. Okay. So first, we are doing an experiment. Yes, rolling a die is an experiment, so the first one is correct. Next, the experiment has more than one outcome. So what are the different outcomes of rolling a die? So we know that the different outcomes are 1, 2, 3, 4, 5, 6. Great. Next, the outcome is unknown in advance. So yes, when you're rolling a die, you don't know what would be the outcome. Okay, so great. And if we repeat the experiment, we won't necessarily get the same result. So of course, if you roll a die and you get an outcome, for example, 3. So if you're rolling again the die, you won't necessarily get, again, 3. Okay, of course you can get 3, but not necessarily. Okay, so great. So this is how those four components work. Okay, now, in order to create a probability model, we need to define some important definitions, and that's what we're going to do now. Okay, so let's start by the first definition. So the first definition is what we call the sample space. So what do we mean by sample space? So sample space, that's this set of all possible outcomes of an experiment. I'll give you an example, of course. So let's start by the notation. So how we denote the sample space? So the notation is what we call the capital letter omega. That's the Greek letter omega. And an example. So if we go back to that classic example, so rolling a die. So what is the sample space of the experiment rolling a die? So again, we use the notation capital omega, and all the different possible outcomes of rolling a die, we know that it's 1, 2, 3, 4, 5, and 6. And then we use also what we call the curly brackets. Okay, so that's how we denote omega with the different outcomes. So that's what we call curly brackets. Okay, now please notice that sets in general, so let me write it here, sets in general are collections of objects where repetition and order are ignored. What do I mean by that? So for example, if instead of writing omega is 1, 2, 3, 4, 5, 6, okay, you write it as 2, 1, 3, 4, 5, 6, that's exactly the same. Those two are equivalent, okay? And even if you write twice 6, okay, that's exactly the same. And therefore, in general, we said that repetition and order are ignored. You don't need to repeat objects that appeared already in the set. And even if you change the order, that's exactly the same. So now we are going to start talking about the second definition, sample point. Okay, so what is a sample point? A sample point, it's an outcome, only one, of the experiment. So what is the notation? So the notation is again a Greek letter, omega, but small omega. Okay, so that's omega compared to the capital omega that we saw in the previous page, okay, and that represent the sample space, okay, so that's what we call the small omega, capital omega, okay, so for the sample point, we're going to use the small omega. Okay, so for example, again, rolling a die. So can you think about a sample point? So I hope that yes. So for example, omega can be 1, it can be 2, it can be any value from the sample space, because the sample space is what? The sample space, if you remember, represents all the possible outcomes of the experiment, okay? So it can be any value from 1 to 6. Okay, so now that we finished definition 2, we are going to start talking about definition 3, cardinality of a set. So what is the cardinality of a set, okay? So this is the measure of the number of elements in the set. So let's see. First, I'd like to write the notation. So the notation is just 2 bars, okay? I'll show you with an example how we use that, okay? So for example, suppose that we have a set 2, 4, and 6, okay? That's a set with 3 elements, 3 objects, 3 elements, okay? And now I'd like to ask what is the cardinality of this specific set? So how many elements do we have here? 3. That's the answer, okay? Another example, so suppose we are talking about tossing a coin, and the 2 elements are H, heads, and tails. And now I ask you, what is the cardinality of this set? So how many elements do we have here? Exactly 2. Another example, so if I ask you, what is the cardinality of the sample space of rolling a die? So that's equivalent to asking, what is the cardinality of 1, 2, 3, 4, 5, 6? And that's exactly 6. Okay, so that's basically what cardinality means. Next, we are going to talk about what is an event. So an event is a subset of the sample space. Okay, so what is the notation in general? So the notation, we use capital letters. It can be A, B, C, and so on, okay? Let's start with a few examples, okay? So again, rolling a die. Suppose that A represents the event outcomes. So what are the different elements in A? So A we have 2, 4, and 6. Okay, those are the only event outcomes in the sample space that represent the experiment rolling a die. Suppose that we denote B as the odd outcomes. So what is B? 1, 3, 5. Okay, so that's basically what an event is. And if you think about it, A is a subset of the sample space. Okay, in this case, A is a subset of 1, 2, 3, 4, 5, 6, because any element here belongs to the sample space, and even here. Okay, I'd like to talk about the empty set. The empty set is an event. Okay, that's an example, another example. Okay, and what the empty set represents. So that's an event that doesn't contain any element. You'll see later on why it's important to talk about the empty set, but for now, believe me, there is an event that is called the empty set. Okay, so that's an event that doesn't contain sample points. And the notation for that is, there are 2 notations. You can use one of them. So that's the first one. Another one is empty brackets. Okay, so you can use one of those 2. Great. So now, before we continue, I'd like to talk about how do we use events in general. So there is a terminology that I want to clarify this now. So the terminology in general says that we say that an event occurs if and only if the outcome obtained from the experiment appears or belongs. Let's say that it appears. It's even better. In the event. I'll explain what do I mean by that. So for example, when exactly do we say that the event occurs? So let me show you an example. Suppose that, again, the example is rolling a die. Now, we define A, the event A, to be an even outcome. So we know exactly how to write A. What do we have in A? So we have 2, 4, and 6. Now, we are doing the experiment. So we are rolling a die, clack, 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 and suppose that we get 4. So by rolling the die, the result that we obtain is 2. Oh, 4, 6. It's not very important, but suppose that we get 2. Now, 2 belongs to A. And therefore, we say that A occurred. Okay, so that's basically what we mean by saying that an event occurred, yes or not. Okay, so let's do another example. Suppose now that, again, we are rolling the die. But now we get 5. So 5 doesn't belong to A. And therefore, we say that A didn't occur. And that's all. Okay, so now I'd like to do a bigger example. Okay, so here's the example. Again, we're going to change it, okay? Don't worry about it, but we start with the easiest examples, and then we'll move to more advanced ones. Okay, so again, rolling the die. Now, we know that the sample space again will represent all the different outcomes of the experiment. So 1, 2, 3, 4, 5, and 6. Suppose that I define A to be the even outcomes. B, an outcome less than 2. C, positive outcomes. And D, outcomes greater than 5. Okay, so here I want you to write A, B, C, and D explicitly. Okay, so what are the different elements in A, in B, in C, and in D? Okay, so here's the solution. So what do we have in A? So we already saw that on the previous page. A represents the even outcome, so the experiment is rolling a die, so of course it needs to be 2, 4, and 6. B, an outcome less than 2. So if we look at the sample space, less than 2, we have only one element, and that's exactly 1. C, positive outcomes. Positive outcomes, all the elements on the sample space are positive, therefore we need to write all of them. 1, 2, 3, 4, 5, 6. And by the way, that means that C equals 2 omega. D, all outcomes greater than 5. Now, greater than 5, so it means that we don't need to include 5. But then after 5, we have 6. 6 is even, and therefore we need to go to the next one, but we don't really have the next element. Okay, and therefore we don't really have anything in D. That means that D is the empty set. Okay, I hope it's clear now. I want to show you more examples of different sample space. So till now we saw only one example, rolling a die. But let's try to complicate a bit. So more examples of sample space. Again, sample space represent the different outcomes of the experiment itself. So let's start by first one. So a coin toss. So what are the different possibilities, different outcomes? So we know that if we toss a coin, the only two possibilities are heads and tails. And if I ask you, what is the cardinality of the sample space? So what do we mean by cardinality? How many elements do we have here? That's exactly 2. Okay, let's continue. Suppose now that I complicate it a bit, and now I'd like to talk about tossing 2 coins. So now, what would be omega? So omega here, now that we toss 2 coins, there are 4 possibilities. First one is that we get head and then tail. Next one is that we get tail first and then head. Another possibility is that we get tails and then again tails. And last one, heads and heads. So here, if I ask you, what is the cardinality of omega? So you need to answer that we have only 4 options, 4 elements. Okay, now let's talk about rolling 2 dice. Okay, let's try to write the first elements. So if we roll 2 dice, what are the different elements? So 1, 1, 1, 2, till 1, 6. That's the first roll. But then, 1, 6, sorry. But then, we can get also 2, 1, 2, 2, till to 6. Then we continue here till 6, 1, till 6, 6. So how many elements do we have here in omega? That's equivalent to asking, what is the cardinality of omega? So here, if you think about it, you have 6 elements times 6, okay? Meaning that you have exactly 36 elements. Meaning that the cardinality of omega is 36. By the way, if we define A to be the sum of the 2 dice, is at least 10. So in this case, if you want to write A explicitly, in this case we need to understand that A has exactly 6 elements. 4 and 6, 6 and 4, 5 and 5, 5 and 6, 6 and 5, 6 and 6. And that's all. Let's just check that those elements corresponds to the definition of A. The sum of the two dice is at least 10. So 4 and 6 is 10. Okay, so 4 plus 6 is 10. So it's of course at least 10. 6 and 4 also is 10. 5 and 5, of course, 10. 5 and 6, that's 11. Okay, and of course 11 is at least 10. And again, 6 and 5 is 11, and 6 and 6 is 12. Okay, so those are the only elements that belongs to A. And if I ask you what is the cardinality of A, so how many elements do we have in A? 1, 2, 3, 4, 5, and 6. So the cardinality of A is exactly 6. Okay, so that's all for those examples. Now we are going to talk about the Venn diagram. Okay, so what is a Venn diagram? So a Venn diagram in general is very useful in visualizing relations between finite events. And in the Venn diagrams, there are two objects. So first, we have that represent general events. Okay, let me just show you an example. We'll do a more complicated one in a few seconds. So let's draw a rectangle. Okay, so this rectangle represents omega, all the different possibilities, and then we can draw a circle that represents a subset of omega, meaning an event. Okay, I'll show you an example and you'll understand why it's very useful. So let's continue with an example. So suppose that you're rolling a die again, and we define A to be an outcome less than 3, B and an even outcome less than 6, and C, the outcome is 6. Okay, now let's write A, B, and C. That's the sample space, all the different possibilities of all different outcomes of rolling a die. Okay, so less than 3 means that we have only 1 and 2. B, an even outcome less than 6. So we already know what are the different even outcomes. It's 2, 4, and 6, but here it needs to be less than 6, meaning that we have only 2 and 4. The outcome is 6. So only 6. That's the event. Okay, great. Now we need to draw the Venn diagram. So again, we draw a rectangle, then we draw the circles. So here we have C. In C we have only 6. And also we have A and B. But be careful when you draw the two circles here. You need to notice that 2 belongs to A and also 2 belongs to B. And therefore there needs to be an intersection between those two events. Okay, so this is why I draw it like that. So here we have A, here we have B. Okay, in A we have 1 and 2. So let's write here 1 because 1 belongs only to A. 2 belongs also to A, but it belongs also to B. And 4 belongs to B, but not to A. And therefore I write it here. And in the end, you need to remember that the rectangle represents all the different possibilities, okay, of rolling a die. So here we have 1, 2, 4, and 6. So what do we have out of those 3 events? So we have 3 and 5. So if you think about it, by using the Venn diagram, we visualize all the different events, and that's going to help us prove some of the theorem in the next lecture. Okay, you'll see why, and you'll see that it's very useful, but only in the next lecture. Okay, now I'd like to talk about events operations. Okay, so events operations. Let's start by the first one, union. So what is the union operation? So the union of two events, A and B, is an event containing all elements that belongs to A or B, possibly both. Okay, before I give you an example, let's start by the notation. So the notation. So if I say A union B, so we denote it as A, we use this symbol that represents union B. So again, A union B. So for example, suppose that I want to compute the events 1 and 2, union the events 2 and 3. So this equals to all the elements in A, or in B, or in both of them. Okay, so in the end we get 1, 2, and 3. Okay, please remember that you don't need to write 2 twice. Okay, we said that we don't need to repeat the same element more than 1 time. Okay, please notice also that in general, A union B equals to B union A. So A, many times instead of saying union, we just say or B. Okay, A or B, that's exactly the same as B or A. Okay, great. Now let's use the Venn diagram to try to visualize the union operation. So I'm going to do 3 different Venn diagrams. Okay, let's say that A looks like that and B looks like that. So here you can see that there are a few elements that belongs to A and also to B. Okay. So when I say A union B, you need to take into account all the different elements of A or all the elements of B and even those that are in both of them. Suppose that A is a subset of B. So this looks like that. A is a subset of B. By the way, the rectangle again represents omega. So when I say A union B, so you need to take into account all the different elements of A, all the different elements of B, and all the elements that are also in A and also in B. In this case, A is a subset of B, so all those elements belongs to A. So in the end, A union B, that's exactly what we draw here in red. Okay. Suppose that the two events, A and B, looks like that. What is A union B in this case? So what is A union B? A union B, that's all the elements in A, or all the elements in B, or all the elements that belongs to A and B. But in this case, there are no elements that belongs to A and B, and therefore that's A union B. Okay, that's the first operation, union. Next, we are going to talk about intersection. So intersection of two events, A and B, consists of all the elements that are both in A and B. Okay, so again, let's start with the notation. So the notation here is A intersection B. By the way, many times instead of saying A intersection B, it's too long, so we say A and B. When we talk about the union, we say that instead of saying A union B, we use many times the word or. Okay, so here intersection, when you're talking about intersection in general, instead of saying A intersection B, we can say A and B. Okay, so for example, suppose that we want to find the intersection of 1 and 2 and 2 and 3. So the question that you need to ask yourself is, what are the elements that are in A and also in B? So in this case, I hope that you understood that it needs to be 2. Okay. Also here, please notice that A and B, that's exactly the same as B and A. Okay. Now let's do the same as we did with the union operation. Let's draw 3 different Venn diagrams and understand how it looks like, the intersection operation. Okay. Okay. Suppose that A and B looks like that. And I ask you, what is the intersection of A and B? So that's exactly the blue area here, because those are the values here, those are the elements, sorry, that A and B are sharing. Okay, now suppose that A is a subset of B. That means that A is here and B is here. So what are the different elements that A and B are sharing? That's exactly A. So in this case, A and B equals to A. And suppose that A and B looks like that. So what is A intersection B? So in this case, A intersection B, if you just look at the Venn diagram, I hope that you notice here that there are no elements that A and B are sharing, and therefore A intersection B needs to be the empty set. Okay, great. So that's how we can visualize the intersection by using the Venn diagram. Next, I'd like to talk about the complement operation. Okay, the complement of A is the event of all the elements that are in omega, but aren't in A. So again, let's start by the notation. So there are 2 ways to denote the complement of A. In this class, we are going to use this notation, the complement of A. So we have just a bar here, A. So again, the complement of A. There's another way to denote it as A, C, small c here, but in class we're going to use this notation. Okay, let's do an example just to understand what complement means. So here's the example. Suppose again that we're talking about rolling a die. 1, 2, 3, 4, 5, 6. And A equals to 1, 3, and 5. Now, if I ask you, what is the complement of A? Those are all the elements that belongs to omega, but not in A. So that means that you need to verify what are the elements that are in omega, but not in A. And in this case, I hope that you figure out that those elements are 2, 4, and 6. By the way, if you think about it, that's all the odd outcomes. And therefore, when I ask you what is the complement of A, that needs to be the even outcomes. Okay? Great. I want you to notice that, first of all, if you just take A intersection, the complement of A, you need to get what? Think about it. You need to get the empty set. Why? What are the elements that belongs to A and not to A? There are no elements that belongs to A and not to A. And therefore, we get here the empty set. And if I ask you what is A union, the complement of A, all the elements that belongs to A or belongs to, do not belongs to A. Okay? So in this case, you'll get omega. That's exactly all the elements in the sample space. And if I ask you what is the complement of the empty set, so what are all the elements that doesn't belong to the empty set? That's exactly omega. And what is the complement of the sample space? So what are the elements that doesn't belong to the sample space? There are no elements like that, and therefore that's the empty set. Okay, now I'd like to explain how to visualize the complement operation by using a Venn diagram. So again, we need to draw a rectangle, and now suppose that A looks like that, and that's the sample space. Now, when I ask you what is the complement of A, you need to understand that the only thing that you need to do is just look at A and then ask yourself what are the elements that are not in A but still in the sample space. So all the elements that are not part of A but still in the sample space, that's exactly the elements that are here, the blue area. That's exactly the complement of A. Okay, in the next part, we are going to talk about an example that covers all the different operations that we talked about. So let's do the example. Okay, so again, let's say that omega is 1, 2, 3, 4, 5, 6. And A equals to 1 and 5. B equals to 2, 3, and 5. And C equals to 3 and 6. Now here's the question. I want you to find, compute, or maybe instead of compute, find A union B, A intersection B, A intersection C, the complement of C, the complement of A and B, the complement of A union the complement of B, the complement of A and the complement of B. Last one, the complement of A union B union the complement of C. Okay, so let's do that. Okay, so let's see. A union B. So A union B, we need to take all the elements that are in A and B and even both of them. So what do we get here? So we have A is 1 and 5, and B is 2, 3, and 5. So what do we get? 1, 2, 3, and 5. Okay, now A intersection B. All the elements that belongs to A and B. Okay, A and B, so let's see. The only element that belongs to A and B is 5. Next, A and C. All the elements that belongs to A and C. So if you look here, 1 and 5, 3 and 6, there are no elements that belongs to A and B, and C, sorry, and therefore that's the empty set. Great, the complement of C. So all the elements that belongs to the sample space, but not part of C. So C is 3 and 6, and therefore the complement of C is 1, 2, 4, and 5. Great, let's continue. So the complement of A and B. Let's find first the complement of A and B, but we already found it. It's 5. So the question here is equivalent to asking the question, what is the complement of 5? And the complement of 5 is 1, 2, 3, 4, and 6. Let's continue. What is the union of the complement of A? Union the complement of B. Okay, so the complement of A is the complement of 1 and 5. Union, what is the complement of B? So that's the complement of 2, 3, and 5. Okay, so the complement of 1 and 5, that's 2, 3, 4, and 6. Union, the complement of 2, 3, and 5, so that's 1, 4, and 6. So the only thing now that we need to do is to take the union of those. So what do we get? 1, 2, 3, 4, and 6. Next, the complement of A and the complement of B. So the complement of A we already computed, that's 2, 3, 4, and 6. And the complement of B also we computed, 1, 4, and 6. So now if we take the intersection of both of them, what do we get? We get 4 and 6. Great. Last one, the complement of A union B union the complement of C. So the complement of A we already computed, that's 2, 3, 4, and 6. Union B, that's 2, 3, and 5. Union the complement of C, also we already computed, it's 1, 2, 4, and 5. So if we take the union of those three events, what do we get? 1, 2, 3, 4, 5, and 6. And that's exactly what? The sample space. Okay, so that's all for this example. Next, I'd like to talk about what we call disjoint events. Okay, so what are disjoint events? So here's the definition. Two events, A and B, are disjoint if they don't share any element. By the way, that's exactly the same as saying that A and B, A intersection B, equals to what? The empty set. Okay, let me show you why. Suppose that we draw the Venn diagram, and here are the two events A and B. So as you can see, those two events don't share any elements. That means that if you take the intersection of A and B, that's the empty set. And that's what we call disjoint events. In this case, A and B equals the empty set. Okay, for example, we already saw one, yes, but let's just remind ourselves. If we are talking about rolling a die, and A represents even outcomes, and B represent the odd outcomes, then A and B are disjoint. Why? Because if you think about it, A, if you write it explicitly, A is 2, 4, and 6. B is 1, 3, and 5. And you can see that they don't share any elements. And therefore, they are disjoint events. And that's exactly the same as writing A and B equals to the empty set. Okay, now I'd like to show you more properties of those operations that we talked about. Okay, so here are the different properties that you should notice when you solve different questions. First, A union the empty set. So if you take A and you add to it the empty set, so of course you need to get A in here. If you take A intersection the empty set, so one belongs to A and also the empty set, that needs to be the empty set. If you take A union the complement of A, so you cover all the sample space. But if you take A and the complement of A, so now there are no elements that belongs to A and not A. That means that that equals to the empty set. Next, if you take A and you add to it the sample space, so you'll get the sample space. But if you take A and you take the intersection with sample space, so what are the elements that belongs to A and the sample space? That needs to be A. And if you take A intersection A, what are the elements that belongs to A and A? That's A. And also, what is the union of A or A? What are the elements that belongs to A or both of them? That's exactly A. Now, I think it's best that after finishing watching those videos, you should try to visualize it with the Venn diagram and verify that all of those properties hold. Okay. Now I'd like to talk about what we call De Morgan laws. So there are two laws that you should remember that you can use each time you want to solve an exercise. So the first one says that if you take the complement of A union B, that's exactly the same as taking the complement of A and the complement of B. The second one says that if you want to take the complement of A intersection B, that's exactly the same as the complement of A or the complement of B. So the best way to understand why it's true, you should use, it's not a proof, but it's going to give you some intuition why it's true. You should use the Venn diagram. So for example, here, you can draw two Venn diagrams and verify that you get the same picture in the end. So let's do it, okay? So let's draw the complement of A union B, and here I like to draw the complement of A and the complement of B. So in the end, if we get the same image, the same picture, so we can say that both of them are equals. Okay, so suppose that A and B looks like that. Okay, now what is the complement of A union B? So we already saw in class that the complement of A union B, that's exactly everything that is in A, everything that is in B, and even in both of them. But when I say the complement, that's exactly what doesn't belong to A union B, but still in the sample space, meaning everything that is out of A union B, everything that is part of the blue area. So that's A union B. Now, we hope that when we are going to compute the complement of A and the complement of B, we need to get the same image. Okay, the complement of A. So the complement of A, that's exactly everything that is out of A. The complement of B, that's everything that is out of B. Now you need to remember that in the end, you need to take the intersection. The intersection means that there's all the elements that belongs to the blue area and the red area. And if you just look here, you'll notice that that's exactly this. And I hope now that you see that you get exactly the same events, okay? So you can do the same for the second one. And in general, you can also, those formula works for more than two events. So in general, for three events, A union B union C, complement of that, that's the complement of A and the complement of B and the complement of C. And if you take A and B and C and you ask about the complement of it, that's the complement of A union the complement of B union the complement of C. So you can just remember those formulas that instead of just trying to memorize them, think about it like that. The bars are break into two and you need to switch the sign. So in this case, for example, one, think about it, it's a complement of A. So the bars are still here, but we switch the sign from union to intersection. Okay, and same for here. Okay, so that's the way that you can remember that. Now, we'll finish the lecture by talking about the last definition. What is a subset? Okay. Okay, so A is a subset of B if every element of A is also an element of B. Notation. So saying that A is a subset of B, how exactly we denote it? So A is a subset of B. That's how we denote it. And if you want to draw it Venn diagram, so we already saw that. So A is a subset of B, looks like that. Okay, now some properties. So if A is a subset of B, then if you take A union B, you need to get what? You need to get B. Just look at the Venn diagram here. All the elements that are in A or in B or in both of them. That's exactly B. And second, if you take A intersection B, you'll get what? A. What are the elements that belongs to A and B? That's exactly A. And that's all for lecture 1. I'll see you on lecture 2.